Here we're going to apply the variation method in order to describe molecular orbitals. We're going to go in some detail and see exactly how one does this. In general, if you recall, the variation method is that one takes a trial wave function that has some parameters in it, then adjusts those parameters in order that the energy you calculate with a trial wave function is minimized. That set of parameters that minimizes the energy is the best set of parameters, will give you the best wave function and best energy. So let's try that out. Let's start here with this trial wave function, phi, which will be a linear combination of a basis set wave function psi j. So psi j are the basis set, and the phi here is the trial wave function. Okay, and then what we're going to do is to get an expression for the expectation value of the energy. That's just this integral here. And then we're going to take the derivative of energy with respect to the parameters. The parameters here are these mixing coefficients, how much of each one of the basis set we're going to add in to the trial wave function. All right, so let's try that. We'll just reproduce this here. So our trial wave function phi will be a linear combination. And let's say we have I equal 1 to n. So we have n basis set functions. This will be Ci times psi I. And the psi 1, psi 2, psi 3, and so on are the basis set. All right, so what we want to do is to calculate the expectation value for energy. We said that's this integral here. We're now using the trial wave function. We have the Hamiltonian for the system. That's that integral. And then for normalization purposes, we divide by this integral here. All right, well, let's substitute in what our trial wave function is. And by the way, we've chosen this basis set so that we can evaluate these integrals with h operating in this basis set. We can then calculate, actually do that. These are eigenfunctions of this Hamiltonian operator here. And similarly down here, we know what the wave functions are, so we can normalize it. All right, so let's go ahead and substitute that in, that expression for a trial wave function. This is the sum over, I'll omit the thing here. This is I equal 1 to n, assumed here. C sub I, psi sub I. This is a Hamiltonian. Let's change the subscript so we don't get confused. We'll make this Cj, psi j. All right, and we can always change the subscript. And then we're going to divide this by that normalization, which will be the sum over I, C sub I, psi sub I, and then again sum over j, C sub j, psi sub j. So there's the integral. These two integrals, and so far so good. Let's sort of rewrite this one here. We'll change the notation. That's what most everybody does. So the sum over Ci, psi I, h, sum Cj, psi j. All right, these are constants, so we can pull them out. Sorry, this is a constant, so when you operate h on here, that is pulled out, so this is just h operating on here. This then will be a product, so you can rewrite this as the sum over I, sum over j, C sub I, C sub j, times the integral of psi I, h, psi j. All right, so you just sort of pull out these constants and operate on the Hamiltonian in here, and this is what you get. And for convenience sake, we're going to denote this integral as I, j. So that's just a symbol for that. Similarly, for this denominator term, let's just write that out, sum over I, Ci, psi I, and this then is just the sum for j of Cj, psi j. And again, we multiply this out. We'll just have a double sum here, sum over I, sum over j of this integral, psi I, psi j, and, oh, sorry, I forgot the c's there. that'd be Ci, Cj, this integral, psi I in psi j. We're going to call this Sij. All right, so we don't have to write those integral symbols. Hij is this psi I here, psi j here with the Hamiltonian in the middle. Sij is the psi I times psi j. Now you remember in the previous lecture we called this the resonance integrals here, and these are called overlap integrals. All right, so with that simplification, it doesn't simplify much, but it did simplify a little bit. We can write that the energy, the expectation value of the energy, is equal to sum over I, sum over j, Ci, Cj, times Hij. And that's convenient, we rewrote that. And then the numerator will be just the sum over I, sum over j, Ci, Cj, Sij, that overlap integral there. Let's multiply this through here. So I'll take that, put it over there. So, and I'll keep writing those E energy times sum over I, sum over j, Ci, Cj, Sij. That's equal to this double sum here, Ci, Cj, Hij. So far, so good. Now let's take the derivative with respect to the parameters. Remember, that's what we're going to do. We're going to take the derivative of energy with respect to various parameters. So let's choose out of these values. I can go from 1 to n, and j goes from 1 to n. Let's choose one particular value that we're going to take the derivative of. Let's call that particular value k. So let's take the derivative of this side with respect to the kth parameter. That's one particular one within 1 to n. I, when you sum these up for 1 to n, eventually I will equal k. And we're taking the derivative with respect to k. All right, so that'd be the derivative of this times sum of I, sum of j, Ci, Cj, Sij. Take the derivative of the other side with respect to this particular value of the parameter k. Remember, that's what we're doing. So these are adjustable parameters, the c's, the coefficients. So we're taking the derivative of both sides of the equation with respect to k. So this would be the sum over I, sum over j, Ci, Cj, Hij. All right, so this are two terms here is 1 and 2. So we'll do I think that's a chain rule. First times the derivative of the second. So E times the derivative with respect to this particular parameter ck of the double sum I and j, Ci, Cj, Sij. And that's equal to, well, we'll just leave this as it is. No, actually, the first times the second, first times the derivative of the second plus the second. So this would be the double sum, sum over I, sum over j, of C sub I, C sub j, Sij, plus the derivative. So first times the derivative of the second plus the second times the derivative of the first. So this then would be how E changes with that particular value, or the particular value ck. That is equal to, and just let me put that down there, that's equal to that, so I don't have to rewrite it because I've run out of room here. Okay, now what we want is to make the derivative of the expectation value with respect to this particular parameter. We want this to be equal to 0. So if that's equal to 0, this whole term is 0, and that means that we're left on the left-hand side with just this term, and on the right-hand side with just this term. So by taking the derivative of both sides here, set the derivative of the energy with respect to k equal to 0, that sets restraints on what these values of the coefficients are and what the energy can be. All right, so that's how we cleverly put in taking the derivative of energy with respect to parameters and set it equal to 0. So what we're left with is the expectation value of energy times the derivative with a particular coefficient k of this double sum, Ci, Cj, Sij. That is equal to the derivative with respect to that same coefficient times the double sum of Ci, Cj, Hij. Okay, well, let's take the derivative inside here and note that Sij and Hij, what were those? Those were just these integrals here, and these will just be numbers because we've chosen our basis set so that we can evaluate these integrals with this Hamiltonian. We know what the basis set is, so these are just numbers. These are integrals, definite integrals, they're numbers. So they're constants and they don't depend on ck, so we can pull them out. So this can be rewritten as the expectation value of energy times the double sum, I and j, of Sij as a constant times the derivative with respect to ck of Ci, Cj. And the same way here, we can pull this inside, and this is just a number, so we can pull that out. So this is just this double sum over I and j of S Hij times the derivative with respect to ck of Ci, Cj. Let's take a closer look at this term here. Let's write this, say, when I is equal to j is equal to k. So in this term, this goes from 1 to n, and eventually it will become I and j equal k. So in that case, this term will be actually just be a single term because it's a single value of I and j. So this will just be skk times the derivative with respect to ck of ck times ck. All right. Now let's consider the case where I is not equal to j, but j is equal to k. In this case, that should be i's. Now, not writing very clearly tonight, so let me, I is not equal to j, but j is equal to k. So when j is equal to k and I is not equal to that, this will be the sum where I is not equal to k of S ik times the derivative with respect to ck of Ci, Ck. And now let's make j not equal to I, but I now is equal to k. So that you give terms there where j is j is not equal to k, or j is not equal to I, which is equal to k. This would be the skj times the derivative with respect to ck of ck, cj. So those are the three kinds of terms you have in here. And it's the same thing here. So here you would have hkk times the derivative with respect to ck. When I is equal to j is equal to k, it'd be ck. Here you would have the sum with the same conditions, I not equal to j, but j is equal to k. You would have the sum, I not equal to k, of that'd be h, we're doing h here, hik, the derivative with respect to ck of ck. And similarly, when j is not equal to I, but I is equal to k, you would have a sum of j not equal to k of hkj, the derivative with respect to ck of cj. So those are the terms there, and those are the terms there. The terms over here, of course, are multiplied by energy. Okay. We now make the observation that Sik is equal to Sik is equal to ki. In other words, if you have, say, I and T, if you have 1 and 3, S13 is equal to S31. Why is that? Well, if we remember what S is just this integral, psi I, psi j, and this essentially is a real number because you're taking the wave function times complex conjugate. And to make things much more easy, let's say a basis set, and these are real. All right, so if they're real functions, that means that it doesn't matter whether you take the complex conjugate or not. So let's make that an assumption. Make things easier so that it doesn't matter whether you have 1, 2, or 2, 1, or 5, 6, or 6, 5, they're the same. And also, since the Hamiltonian here is Hermitian, it doesn't matter whether you have H12 or H21, they're both equal. So if that's the case, if they're both equal, then you can simplify this a little bit. Let's just see that. So that first integral, let's write down all those terms. That was skk times the derivative with respect to ck of ck times ck. Well, that's just equal to, well, derivative of that is just 2. So this is 2 skk times ck. Let's do the next one. This was the sum over I not equal to k of sik times the derivative of cick with respect to ck. That's just equal to the sum, I not equal to k, of sik times ci. Derivative of that, just ci. And similarly, the sum of j not equal to k of skj, the derivative of ck, cj, with respect to ck, that's just equal to the sum, j not equal to k, of skj times cj. Now, what I'm going to do here, these are dummy variables, and I can call them anything I want. And so I'm going to call them, instead of j, I'm going to call them I. So this now is the sum of I not equal to k. I'm free to do that because it's a dummy variable. ski times ci. Well, look at here. Okay, sik is equal to ski, and we have the ci's there. So these two can be combined as 2 times the sum of I not equal to k of sik ci. See how you combine those two as dummy variables? And now we look at this even further. We have this term here, okay, and we have this term here. All right, so this is for all values of I not equal to k, and this is the value where I is equal to k. So what we're doing is we're adding these things up. Remember, that's what we're doing here. So we just took this, and so we put that all out, and we're adding them up. So this term, we can include the value of k by just saying that this is the 2 times the sum of sik, where I now can equal k. I goes from 1 to n, because when it equals k, we included this term, times ci. All right, so that's what that term is. And let's go ahead and put back the energy. So I'm going to put back the energy term there. So this is the energy. Okay, so that's that. Now how about the right-hand side of the equation? Okay, the right-hand side, here it is. We have all these terms. Maybe you can see this just almost exactly like this, but instead of the sik, we have hik. So without going through the details, I think I can immediately write this as 2 times the sum of I equal 1 to n of hik ci. And remember, K could be 1, 2, and so on up to N. So it's just one of these particular values. That's what K is. All right, so there's our equation. Look, we can cancel out the 2's here. And let's let's bring this over here so we can set everything equal to 0. So what we have is 0 is equal to the sum as I equal 1 to N of HIK C, that should be a subscript there, HIK CI minus E times the sum over, let me put that E inside, it'll make things a little easier. So if I go up here, see, we're just multiplying E times the sum. Let's put that E inside. We'll multiply through by the sum. Okay, so this will just be the sum I equal 1 to N of E S I K times C I. Okay, and again, K could be anything. K is a particular value, and the sum I runs from 1 to N. And we can rewrite this still further, simplify it as the sum, I equal 1 to N. We can put both these things inside the sum and sum them up. This would be HIK minus CI, times CI, sorry, getting a little late, CI minus E S I K times C I. All right, finally, these are called the secular equations. All right, so just to recap what we did, we just briefly, just so we don't get too confused here. We started with this trial wave function here. And we put that trial wave function into an expression for the expectation value of energy. And we did some calculations here, or no, sorry, not calculations, we did some algebra here. And then we said, all right, let's take the derivative with respect to a particular value of the parameter, Cj, those are those expansion. These are the ones we want to vary to minimize energy. And we get this expression, and we set this value, how E changes with that parameter, set that equal to 0. And with that, we get these secular equations here. And these are values. If we solve these secular equations for the C or for the energy, those are the values that correspond to the minimum in energy with respect when we took the variation of energy with respect to the parameters. Okay, well actually let's write down. Suppose, say, we have n basis set functions. And that means that K could be 1, 2, up to N. So let's write down for K equal 1. For K equal 1, and just write down, we'll write down a few of these terms. This will be H11 minus E S11 times C1, so I is equal to 1, plus, now I is equal to 2, but K is still equal to 1. This is H21. I made a mistake here, sorry. I pulled out the C term here out there, so sorry about that. So H21 minus E S21, so I is E now equal to 2, so we're writing out this sum for K equal 1, that'd be 21 times C2 plus and so on, that is equal to 0. Let's write down the expression for K equal 2. All right, K equal 2, this would be H and I is equal to 1. So this would be H12 minus E S12 times C1 plus H22 minus E S22 times C2 plus and so on equal to 0. And this all the way goes down to K is equal to N. So this would be H1N minus E S1N. Sorry, this should be C2 there. Cn plus H2N minus E S2N times Cn plus, oh, I'm sorry, this is I equal 1 to n, so sorry. Nah. Probably, okay, C1, C1, C2, 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 and C3, C3, 3. Yeah, what I'm trying to do is to write down this equation on this board. Okay, so here it is. So this is for the K equal 1, the K equal 2, this is the K equal n. And so these are equations that have to be satisfied, and they have to be satisfied for the energy to be, the derivative energy with respect to the parameter has to be equal to 0. Okay? So we got these equations by taking the derivative and set the derivative of energy with respect to a parameter equal to 0. These are called the secular equations, written in compact form. Here they are. But if you actually write them out, keep track of the K equal 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 1, 1, 2, 3, and so on. If you keep track of all those things very carefully, this is what you get. Okay, and again, just to emphasize, everything is known in this equation except for energy and except for the parameter C. The H's and the S's, those are known because we've chosen our basis set functions wisely, so we can evaluate this integral here and also this integral here. And again, we made the assumption that the operators are Hermitian, so Hij is equal to Hji. It doesn't matter which way you take the complex conjugate. And the wave functions are real, so it doesn't matter which one you take the complex conjugate of. They're both real. Okay. So what do we do? I mean, how do we actually get the energies and the wave functions out? Getting the energies mean what are these E's? Getting the wave function means solving for these coefficients, C1 through Cn, because we know what those are, then we could just write down the wave function from here. All right, well, you may remember, or maybe not, from high school, that if all these equations, these are simultaneous equations, you have n equations in n unknowns, C1, C2, and so on, Cn, in addition to the energy, but just say we're solving for Cn, we want those coefficients, and say the energy we'll get in just a minute. In order for these equations to simultaneously be equal to 0, n equations, n unknowns, for them simultaneously be equal to 0, the determinant, this determinant has to equal 0. All right. So let's just do a simple example. Suppose that we have n equal 2. That means we have two basis sets, two functions, basis set functions. All right. So in that case, we'll just have two secular equations. We'll have H11 minus E S11 times C1 plus H12 minus E S12 C2, that's equal to 0. And then we have H21 minus E S21 times C1 plus H22 minus E S22 times C2 equal to 0. We can write this as a matrix equation, H11 minus E S11, H12 minus E S12, H21 minus E S21, and H22 minus E S22. That's a matrix, 2 by 2 matrix, times this coefficient here, matrix C1, C2, that has to equal 0. All right, so I don't know if you remember how to multiply matrix. That one times that one, all right, and that times that has to equal, well, let me just write this as a column matrix here is 0, 0. That's equal to 0. So that times that plus that times that equal to 0. That's that first equation. This times that plus that times that has to equal this matrix element. That's 0. That's the second equation. So we can write this system of two equations and two unknowns as matrix form. And now we look at the determinant. In order for this to be true and for C1 not equal to 0 and C2 not equal to 0, in order for that to hold, or this to be 0, the determinant of this matrix has to equal 0. So H11 minus E S11 and H12 minus E S12 and H21 minus E S21 and H22 minus E S22, this determinant has to equal 0 for a non-trivial solution for this system of equations. If you don't want this to be 0, then this determinant has to be 0. All right, well that certainly is helpful because now we don't even care about the coefficients. We solve this equation, that times that minus that times that, set that equal to 0. We have a quadratic equation in E. We solve that for E, we'll get two roots. It's a 2 by 2 system, so we'll get two roots. The lowest value, because H11, S11, all these H's and S's are known, so we can then just solve this for E, and we'll get two values of E, one value and two values, and then we'll say, okay, the lower value is the ground state, and the one up there is the excited state. With that value of E, we'll go in and plug in here. Now everything in the matrix is known, and therefore we can solve for C1 and C2 when we get the coefficients. So that's how one solves the secular equations. The solution requires that the determinant of this coefficient matrix has to be 0. And so you solve the secular determinant for E, and you get it's an nth root polynomial. So if you have a n by n matrix, when you do this multiplication down the side here, or down the diagonal, you got E times E times E times E. So if you have n columns and rows, you'll get an E to the nth polynomial. And you solve that E to the nth polynomial, take the lowest E as a ground state, you plug that E back into the secular equations to get Cj and so on. And so that's how you do it. Pretty cool. What we'll do next is to actually go through a particular example. This was general, and so we have these, n things. But the next example we'll actually go through, we'll use Huckel molecular orbital theories, the variation theory, for pi electron systems in organic molecules.